Number one, in the population of students, the number of calculators owned is a random variable x, with p of x is equal to 0, which is equal to 0.2. So this means that there is a 20% chance that you own 0 calculators in this population of students. What we should do is we should make a table. So let's make a table for our probability distribution. There are 3 options. You own 0 calculators, 1 or 2. So I need 3 lines. 1, 2, 3. And so let's mark this x, and this is p of x. So you have a 20% chance of owning 0 calculators. You have a 60% chance of owning 1 calculator, and you have a 20% chance of owning 2. So these 3 numbers should add up to 1. So to find a mean, the mean is e of x, that's the expected value, commonly referred to as mu of x. It is equal to x times p of x. It's the sum of all random events times its respective probability. So we start with 0, we multiply it by 0.2, plus 1. The probability of owning 1 calculator is 60%, plus 2 times 0.2, because there's a 20% chance of owning 2 calculators. So this is expected value. Let's write it down below. So 0 times 0.2 is just 0. 1 times 0.6 is, well, 0.6. 2 times 0.2 is 0.4. So the answer is 1. And that is expected. You are expected to, if we were to do this in the long term, on average, we should get 1 calculator per student. So the answer is C. The variance of the probability distribution above. So we need to understand that the variance var of x is the sum of each deviation. So you take the x value minus the mean, which we do have. The mean is this, mu of x, that's mean, squared times its probability. So for example, if you have 0 calculators, you do 0 minus 1, because 1 is the mean. You square that, and you multiply it by the probability, which is 0.2. And you repeat this process for the second random event. So if you have 1 calculator, 1 minus the mean squared times 0.6. And we have the third option, which is 2 calculators. So you do 2 calculators minus the mean squared times its probability. For the middle term, 1 minus 1 is 0, so that just goes away. I'm going to ignore it. And you can just type this into your calculator and use out. The first term should be 0.2 because it's just 1, negative 1 squared is 1. 1 times 0.2 is 0.2. The other option is, or the third term should be 2 minus 1, which is 1. 1 squared is 1. 1 times 0.2 is, well, just 0.2. You add these up, it should be 0.4. So the option is D. And of course, you can just use your calculator. For number 3, we're eating some kind of cereal. My favorite is, Captain Crunch or Cinnamon Toast Crunch. 1 ounce cereal and some random variable would mean C. So let's just say C for cereal. Let's make this green. In milk, let's just call it M. So we know that the mean for cereal is 110. Mean of cereal is 110. And the mean of milk is 140. For breakfast, you eat 1 ounce of cereal. So that's going to be C. With is an and statement, so we add half cup of milk. So we need to do 1/2 M. And they said, let Z be that random variable. So we can call that Z. So Z is C plus 1/2 M. So if I want to find the mean of Z, the mean does exactly what it tells you to do. So you take the mean of the cereal plus 1/2 times the mean of m. So that should be 110 plus 1/2 times 140. A half of 40 is 70. So 110 plus 70 should be 180. So C is our answer. For number 4, number 4, a psychologist studied a number of puzzles that are able to be solved in a 5-minute period while listening to music. Let X be the number of puzzles solved successfully. Okay, so the 4 options are 1, 2, 3, or 4. So you can either solve 1 puzzle, 2 puzzles, 3 puzzles, or 4. So using above data, what is the probability that a randomly selected subject completes at least 3 puzzles? So we need to find probability. Capital X is a random variable. At least 3 means greater than or equal to 3. So I'm going to highlight this. It's just these 2 options. It's either 3 or 4. So it should be equal to the probability of 3 plus the probability of 4. Probability of 3 plus probability of 4, what was given, is 0.3 plus 0.1. That is 0.4. So the answer is B. Number 5, using the above data, find the probability of X is less than 3. So a couple ways to do this. Let's just say that probability of X is less than 3. We already figured out the top part. This is just the complement of part 4. So it's just 1 minus the probability of X is greater than or equal to 3. So this is just 1 minus 0.4, which is 0.6. You can do it like that, or you can add it by saying the probability of X is less than 3 is equivalent to the probability that it's 1 plus the probability that it's 2. This is the probability of 1 or the probability that it's 2. So this is just 0.2 plus 0.4, which is 0.6. Alright, so we are now on problem number 6. Using the above data, the mean of X is blank. So from before, we know that there are 4 columns for the number of puzzles that you can solve successfully, 1, 2, 3, or 4. So what we should do is we should take 1, so E of X, or mu of X, is 1 times 0.2 plus 2 times 0.4 plus 3 times 0.3 plus 4 times 0.1. So 1 times 0.2 is just 0.2. 2 times 0.4 is 0.8. 3 times 0.3 is 0.9 plus 0.4. 2894, so that should be 23, so this should be 2.3. So the mean of X is 2.3. So in the long term, the average number of puzzles solved should be on average 2.3. Cancel solved trains cost 30 cents in a certain vending machine. This is probably back in the 90s. What is the expected value and variance of daily revenue, Y, from the machine if X, the number of cans sold, has expected value of 125? So that means that every day, daily, you're expected to sell 125 cans of soda, and the variance is 50. Okay, so we know that the expected value of X is 125, so this is given. And the variance of X is 50. So we need to come up with an equation for Y, since each can, so Y equals, is sold for 30 cents each. we should just take 30 cents, 0.30 times x. So that's the equation for y. And we need to understand that the expected value for y, the expected value does exactly what it tells you to do. So if y is 0.3 times x, the expected value of y is simply 0.30 times the expected value of x. But we do know what the expected value for x is. The expected value for x is 125, so I can just get rid of that to save some space. It's 0.30 times 125. So you multiply that together, that should be 37.5. Right? So obviously E is incorrect. Now, the common mistake is that most students will probably say that the variance will also get multiplied by 0.30. However, if you recall, the variance does not work that way. The standard deviation does, but not the variance. So the variance var of y is actually your multiplier, your multiplicative factor 0.3 squared, because the variance is the standard deviation squared, times the variance of x. And so that's going to be 0.9 times 50, not 0.3 times 50. So 0.9 times 50 should be 45. Oh, sorry, 4.5. My bad. So 4.5. So 8. A rock concert producer has scheduled an outdoor concert. If it's a warm day, she expects to make a $20,000 profit. So for this problem, you could make a table, or you don't have to. I'm still going to make a table for the joint, the probability distribution. So let's just make a table. So there's some options here. There are 3 options, so I'm going to make 3 lines. Let's just call this x and p of x. So if it's warm, you make a $20,000 profit. And the probability that it's warm is 60%. So there's a high chance that you make good profit. However, if it's cool, you only make a $5,000 profit. And then there is a 25% chance that it is cool. So the last option is you actually lose money, $12,000. So we need to do 1 minus 0.6 minus 0.25 because it's not given. So 0.6 plus 0.25, that's going to be 0.85. So 1 minus 0.85 should be 0.15. And we know that the expected value, E of x, is the sum of the product of each of the random events times its respective probability. So we need to do 20,000 times 0.6 plus 5,000 times 0.25 plus negative 12,000 times 0.15. We could have also subtracted 12,000 times 0.15. That probably looks a lot cleaner. So the expected value, you should just use your calculator. You should get 11,450 E. All right, so number 9, what are we given? We're given that the probability of A is, let me use the red pen here. The probability of A occurring is 0.8. The conditional probability, so probability of B given A is 0.5. So these are given. We need to figure out what the probability of A and B is. So probability of A and B is what we need to find. So if you recall, a couple of things. The probability of B given A, that is equal to the probability of A and B, or B and A, doesn't matter, because it is commutative, over the probability of the second, so of A. So we know, therefore, the probability of B and A is given 0.5. is equal to probability of A and B, which is what we try to find, divided by 0.8. So in order to solve for probability of A and B, we need to do the inverse of divided by 0.8. So the opposite of divided by 0.8 is to multiply both sides by 0.8. So that's it. We just need to do 0.5 times 0.8. 5 times 8 is 40, so that should be 0.4. That's B. Number 10. At this high school, 60% of students have high-speed internet access. So lots of ways to do this. I suggest that you make a Venn diagram, but we can write down the given. So let's say H is high-speed internet access, and M is for having a cell phone, a mobile computing device. The probability of H is 60, so 0.6. The probability of having a mobile device, a cell phone, is going to be 0.3. And the probability of both, so probability of H and M, that's going to be 0.2. All right, so let's make a nice little diagram here. Let's make a rectangle, make 2 circles. Not the best circle. And for some reason, I have an extra one here. All right, so let's start with the middle. The middle should be the AND statement, so 0.2. Let's call this H. Let's call this M. So H and not M should be 0.6 minus 0.2. That's 0.4. Let's clean that up a little bit. So this is 0.4. There's a 40% chance that you have high-speed internet access, but you don't have a cell phone. So this should be 0.3 minus 0.2, which is 0.1. There's a 10% chance that you only have a mobile computing device, a cell phone. So this should be 0.1. If I add up the 2 circles, 0.4 plus 0.2 plus 0.1, that should be 0.7. So then this must mean that it's 1 minus 0.7, which is 0.3. So we need to find the proportion of students that have neither. So the probability statement should be probability of not having high-speed internet access and not having a mobile device. You can write like that, or you can also write it as the complement of H union M. So these two are exactly the same. So that's going to be 1 minus 0.7, which is 0.3. So if I highlight it, we're trying to find this particular area. Sorry, not area, but the probability. So 0.3. Suppose the amount of propane needed to fill a customer's tank is a random variable with a mean of 318 and a standard deviation of 42 gallons. So let's call this random variable x. So we're given E of x is 318 gallons, and the standard deviation of x is 42. So Hank Hill is considering 2 pricing plans for propane. Plan A would charge $2 per gallon. So under Plan A, let's make it green. A, okay, that's not green. A is just $2 times x, so it's 2x. Plan B will charge a flat rate of $50 plus $1.80 per gallon. So it's cheaper by the gallon, but you had to pay an upfront cost of upfront cost of $50. So it's 50 plus 180x. This is per gallon. So we need to find the mean and standard deviation of the distributions under each plan. So let's do part A first. So the expected value always does exactly what you tell it to do. Since A is 2 times x, the expected value of A is just 2 times expected value of x. So that should just be 2 times 318. So that should be 636. Move this slightly towards the right here. I have too much space. It's annoying. Right below. So this is 2 times 318. So that should be 636. So the variance, sorry, not the variance, we need to find the standard deviation of A. So the standard deviation, luckily for us, we're just multiplying here. So the standard deviation does exactly what you tell it to do here. So just 2 times the standard deviation of x. So this should just be 2 times 42, which is 84. Part B, the expected value for B. The expected value for B does exactly what you tell it to do. So it should be 50 plus 1.8 times the expected value of x, which was 318. So 50 plus 1.8 times 318 should be 622.40. $622.40. The variance, however, not the variance, sorry, the standard deviation of B. Since we're adding by a constant, that doesn't affect the standard deviation. So in fact, it doesn't affect the variance as well because they're both measures of spread. We just do 1.8 times the standard deviation of 42. So that should be 75.6. $75.60. So for part B, assuming that both distributions are normal, calculate the probability that B would charge more than A. So I think this is missing a part, but we need to assume A and B are independent. Assume A and B are independent. Otherwise, the variance formulas do not work. So what we need to do is find the probability of B is greater than A. So to do this, we are going to combine these two variables into one singular random variable. So let's move it to one side. So let's move A to the left side. So B minus A is greater than 0. So this is one singular variable. You could give it a name. You can make it C, but I'm going to use the same 2 letters to represent a singular random variable. So a couple things. We need to find x, we need to find mu, which is the mean, and we need to find the standard deviation. So let's write on the side, lowercase x, mu, b minus a, aka mu, and the standard deviation, sigma. So x is just 0, so that's that. For mu of b minus a, the mu is the mean, right? So this is just the mean of b minus the mean of a. And from before, the mean is expected value. So it should be, what was b? Is 622.40 minus 636. So on average, the plan B is cheaper than plan A, but because they're both normally distributed, there's some overlapping. So there are some times when B actually costs more than A. So we need to be careful. So 622.4 minus 636 is a negative 13.60. So the difference is $13.60 between the averages. So now we can write that here, negative 13.60. And then the standard deviation, be careful, sigma of B minus A. We're not subtracting here ever. For variance, we're always adding the variance, right? So we need to take the variance of B and A. So we kind of already did it before. But assuming that you know the standard deviation, right? First of all, we need to use the Pythagorean theorem. So square root. We need to take sigma of b squared, which is the variance of b, plus sigma of a squared. So that's the standard deviation. So you take the standard deviation of b, which we got from above in the green, the 84. So it should be 84 squared plus 75.6 squared. So here you just take out your calculator, crank it out, you should get, see, 113.01. So $113.01. So we know that this is a normal model. So we need to find the z-score. Z-score is x minus mu over sigma. So the z-score should be 0 minus negative 13.6 all over 113.01. So the z-score should be 0.12. Just draw a picture here. And I wrote this kind of big. So we have this. Draw a little hump. The mean was negative 13.6. And we want it to be at 0. That's our little marker. Let's make it blue here. 0 is to the right of negative 13.6. Somewhere over there. We want it to be greater than, so we shade the right side. So we want to figure out when is the probability that the z-score, right, is greater than 0.12. So if we use our table A, this is just 1 minus the probability of the white area over here, this area. It only gives you the left tail. 1 minus the probability that the z-score is less than 0.112. So let's take a look at our formula sheet. Let's scroll down here. So 0.112. If you look on this side, let's use the highlighter tool. 0.1 is here. It is this row. And then we want it to be 0.12. So this is the precision mark, 0.12. They overlap here. So 0.5478. So this should be 1 minus 0.5478. And then you take out your calculator and you calculate what that is. I would suggest, though, that another way of doing this is understanding the fact that, well, this area, this blue area, is the same thing as this red area. So instead of using a z-score of 0.12, we could use a z-score of, what's the z-score? Negative 0.12. So it's easier, in my opinion, if you did the negative z-score. So if you scroll up, the negative z-score should be negative 1 is this row, and then 0.02. It's easier to think of that as the complement of the other one. So the answer should be 0.4522. So this is just the red area, 0.4522. And that is it. So for an upcoming concert, each customer may purchase up to 3 child tickets and 3 adult tickets. Let C be the number of child tickets purchased by a single customer. The probability distribution of the number of child tickets purchased by a single customer is given in the table below. So there's 3 options. You can either buy 0, 1, 2, or 3 tickets for your children. So you can compute the mean. So the mean, if you recall, E of x, the mean, is the sum, sigma, of x times p of x. Here we don't have x, we use c, but it works the same way. So the expected value of c is the sum of each x value. So there's 1, 2, 3, 4 x values times its respective probability. So it will be 0. Let's just do it like this. 0 times 0.4 plus 1 times 0.3 plus 2 times 0.2 plus 3 times 0.1. And then you can take out your calculator, figure out what this is, but this one's just 0. 1 times 0.3 is 0.3 plus 0.4 is 0.7. 0.7 plus 0.3 is just 1. So, on average, in the long term, these customers will buy just one child ticket. Now for the standard deviation, sigma, so this is mu of c, by the way. This is sigma of c. The standard deviation is just the square root. We use the Pythagorean theorem, but here we have 4 random variables here. So we just do 0 minus the mean. So 0 minus 1 squared times 0.4 plus 1 minus the mean, 1 squared times 0.3 plus, we need to do this 2 more times, 2 minus 1 squared times 0.2 plus 3 minus 1 squared times 0.1. And you use your calculator, and you should get 1 ticket as well. So plus or minus 1 ticket. So the expected value of child tickets purchased is 1 ticket with a standard deviation of 1 ticket. So for part B, suppose that the mean and standard deviation for a number of adult tickets is 2 and 1.2. So let's just say A is the number of adult tickets. A is the number of adult tickets. It is a random variable because it's capitalized. And we know that the expected value for A was 2. So on average and long term, they buy 2 tickets. And that makes sense, couples. And the standard deviation is 1.2. SD of A is 1.2. Compute the mean and standard deviation of the total number of adult and child tickets. So we have C and A. So we should just add them up. We don't need to give it a name. Just call it A plus C. So A plus C. You can call it T, I guess. T is the total. Let's give it a name. The expected value of T is just expected value of A plus expected value of C. Expected value of A is 2 tickets for couple, plus that 1 ticket for child that we calculate from above in part A. So that's just 3 tickets. And that makes sense. You expect to buy 3 tickets. And then for standard deviation of T, the standard deviation of T is the square root of the standard deviation of A squared plus the standard deviation of C squared. So that should be the square root of, what was it? For A, it's 1.2. 1.2 squared plus, let's see, it was from above 1 squared. So 1.2 squared plus 1 squared, square root of that should be 1.56. Suppose each child ticket costs $15 and each adult ticket costs $25. Compute the mean and standard deviation of the total amount spent for purchase. Okay, so we should use another random variable. So it's $15 per child, and then $25 per adult. So that one's pretty straightforward. It's 25A plus 15C. Depending on, so A is the number of adult tickets, right? So this is our new random variable. We could give it a name as well, but I kind of don't want to for this one. Let's just find expected value. Let's find expected value of 25A plus 15C. Right. So the expected value does exactly what it tells you to do. So this should just be like 25 times the expected value of A plus 15 times the expected value of C. Sorry for the terrible handwriting here. Let's see. The expected value of A was what? 2? Yeah, expected by 2 tickets plus $15 for one child ticket. So we have 25 times 2, that's 50. So that's going to be 50 plus 15. That should be $65. $65. Okay. So for the variance, let's just stick to green. No, we don't need to find the variance, sorry. We need to find the standard deviation. Standard deviation 25A plus 15C. So for this one, we kind of have to be careful here. There's a constant, the 25 and the 15. So what we should do is we should use the Pythagorean theorem, square root. We need to do 25 times, what was the standard deviation of A? That's 1.2. 1.2 squared plus 15 times the standard deviation of C, which I believe it was 1. Yeah, it was. Times 1 squared. So you can either distribute the square to the 25 and the 1.2. That's what we should do, but if you have a calculator, you can just type it in exactly like that. Or you do 25 squared times 1.2 squared plus 15 squared times 1 squared. So as the final answer, you should get about 33.54. All right, for number 3, a lab test for the detection of a certain disease gives a positive result 5% of the time for people who do not have the disease. The test gives a negative result 0.3% of the time for people who have the disease. Large-scale studies have shown that the disease occurs in about 2% of the population. So let's use some letters here to make it a little bit easier for us. Let's say D is you have the disease. D means you have the disease. And then P means you test positive. Test positive. So make a tree diagram. D for disease, not D. So there is a 2%. So 2% means 2 out of 100, which is 0.02 because you move the decimal place to the left. So that should be 0.02. And then you have a 98% chance of not having this disease. So let's take a look at the other part. A lab test for detection gives a positive result 5% for who do not have disease. So if you do not have disease, there's a 5% chance that you test positive. So that should be 0.05. So not positive means negative. There's a 95% chance that you do not test positive. Now the test gives a negative result 3%, or not 3%, 0.3%. So this one is kind of annoying. I think it's a typo, but I'm going to go by what it says in the prompt. So 0.3% is 0.3 divided by 100. So you move it to the left by 2. So that should be 0.003. So if you have disease, you have a 0.003 chance of not testing positive. So therefore, you have a 0.997% chance of testing positive. What is the probability that a person selected at random would test positive for this disease? So we need to figure out what the probability that you test positive. So that's kind of annoying. Probably a P of P. P of P. This P is not the same thing as this P. So the probability that you test positive, well, let's think about all the branches that are positive, right? This branch test positive, or this branch. So you just find the joint. You do 0.02 times 0.997. That's, you multiply them, right? And because these are disjoint, you add it to the probability that you do not have the disease, but you test positive. So this is 0.05. And then you just take out your calculator and you figure out what that is. So I'm going to take out a calculator. So 0.02 times 0.997 plus 0.98 times 0.05. You should get about 0.06894. So that means that there is a 6.894% chance that you test positive, regardless if you have the disease or not. All right. So we want to find a probability that you don't have the disease given that you are positive, right? So given P. So the probability that you don't have disease given that you're positive. So remember, this is a conditional probability. So it's the probability of you don't have the disease and you are positive, given that you are positive. All right. So we actually calculated the probability that you were positive from above. It was this number. So we can use that to our benefit, 0.06894. So we need to figure out what the branch was. So let me erase all this green stuff. Where we were did not have disease, which is this path. What the heck? Which was this path here. The 0.98. You had a 98% chance of not having disease. So we should write that down, 0.98. Because it is an answer, we multiply it to the probability that you are positive given that you had, if you didn't have the disease. So 0.05. So let's just take out a calculator. 0.05 times 0.98. This should be 0.049 all over 0.06894. Let's use the calculator, divide that by 0.0894. You should get as a final answer 0.71 7108. So that's a 71.08% chance. There's a 71.08% chance that a person selected at random who tests positive for disease does not actually have the disease. So we're on the last problem right now, number 4. US Today gave information on seatbelt uses by gender. The proportions in the following table are based on the survey of a large number of adult men and women in the US. So it's split into gender as the categorical variable and also whether or not they wear seatbelts or not. So let's just find the marginal distribution. Let's just add them up. So the total should be, let's just write total here, and then total over here. 0.1 plus 0.4 is 0.5. I'm going to use the calculator for these. I'm going to add up the column. 0.1725 plus 0.325 should be 0.4975. I don't know why this is, but 0.5 plus 0.4975 is actually not 1. So there is a weird issue here. I think this is a rounding issue. I don't know, does this make sense? But I'm going to go with it. 0.1 plus 0.1725 is 0.2725. 0.4 plus 0.325 is 0.725. So yeah, I feel like there's a rounding error here. Let me just make note of that. There is a weird rounding error. Oh, well, it's also because of the 5 weird rounding error. Okay, so assume that these proportions are representative of adults in the United States and that a US adult is selected at random. What is the probability that the selected adult regularly uses a seatbelt? So we need to find the probability that they wear a seatbelt. Let's just use S means you wear a seatbelt. Wear a seatbelt. And let's just use M for male, F for female. What is the probability that the selected adult regularly uses a seatbelt? The probability of S seatbelt. Well, we knew what it was. It was just the number of male who wears a seatbelt, which is 0.10, plus the percentage of females who wears a seatbelt, which is 0.1725, which we got was 27.25%, so 0.2725. So that one was pretty straightforward. B, what's the probability that the selected adult uses a seatbelt given that they are male? Given it's a keyword, we use the vertical line. So let's find the probability that they wear a seatbelt given that they are male. All right. So we need to figure out what the probability that they wear a seatbelt and they are male over the probability that they are male. The probability that they are male is pretty straightforward. It's just the 0.5. And the probability that they are male and wear a seatbelt is the smaller number, 0.1. So 0.5 divided by 0.1, that's just 1/5. That's 20%. So 0.20. All right, seatbelt given that they are male. All right, part C. What is the probability that the selected adult does not use the seatbelt regularly, given that they are female? Okay, so find a probability that they don't use the seatbelt, given that they are female. Okay, so we need to figure out the probability that they don't wear a seatbelt and they are female over the probability that they are female. So let's do the denominator first because I feel like that's the easiest part. So the probability that they're female, I feel like that should be 50%, but we'll use the number that they gave us, 0.4975, 0.4975. And that's that. The probability that they are female and they do not use a seatbelt regularly is that number, 0.325. So let's just take 0.325 divided by that number. Let's use the calculator. 325 by 4975. Sorry. 0.325 divided by 0.4975. So we should get 65.33. 65.33% chance. So for part D, what is the probability that the selected individual is female, given that they do not use a seatbelt regularly? Okay, trying to spice this up. Probability that they are female, given that they do not use the seatbelt regularly. So complement of S. So, I mean, we just kind of do kind of what we did before. Probably that you're female and you do not wear a seatbelt regularly, divided by the probability that you do not wear a seatbelt regularly. So this time we do the rows instead of the columns. So just erase these marks here. So what's the probability that you do not wear a seatbelt regularly? So it should be like 0.725. 0.725. And the probability that they're female and they do not wear a seatbelt regularly was 0.325. So similar to part C, but we divided by the row total instead of the column total. So that's going to be 0.325 divided by 0.725. The answer should be 0.4483. And then for part E, let's make this blue again. Erase this here, erase that here. So for part E, when selecting the person at random from the sample, are the events using a seatbelt regularly and is male independent? So we're trying to ask ourselves, is the probability, oh, that's not blue, the probability of seatbelt, wearing a seatbelt regularly, is equal to the probability of seatbelt given that you are male, right? So if they are independent, then this must be true. So let's figure out what the probability of wearing a seatbelt is regularly. So the probability of wearing a seatbelt regularly is 0.2725. 0.2725. We need to figure out if this is equal to the probability that you wear a seatbelt regularly and you're male over the probability that you're male. Right? So is this true? So the probability that you wear a seatbelt and you're male, seatbelt and male should be 0.1. So it's 0.2725 equal to 0.10 divided by the probability that you're male. So 0.5. So 0.275, is that equal to, didn't we ever calculate that? That's from part B. Yeah, we did. 0.2. The answer is no. These two are not equal. Because they are not equal, these two events are not independent. So make a quick statement. Therefore, S and M are not independent. I'm running out of space, but you would say like the event using the seatbelt and male are not independent.